When Numberphile released their video on plotting beautiful curves in February 2022, I was immediately inspired and fascinated by the artistic beauty that very simple rules can create. You have not seen it yet? Go check it out, the link is in the description. When getting first into touch with programming in the early 1990s, Turtle graphics and logo were my first programming experience, and I love the language for its simplicity and short commands. It is therefore perfect for this project, and you will find logo code snippets throughout this video. The language is even compact enough to create t-shirts that hold all that is required to reproduce them as part of the design. As I love it a lot, it seems to be time to get a new one soon. The Euler spiral algorithm is very simplistic and yet so mysterious in its results. The core element and sole parameter is the base angle theta. For every iteration, the turtle rotates clockwise theta times the number of steps it has already taken, and then moves a given step forward until the total number of iterations is reached. For an extensive introduction, please watch the Numberphile video. So first, let's have a closer look at the base element. It is basically two spirals that connect over a long stretch and is introduced in the Numberphile video with a theta value of 1. To get a sense of direction, we activate the turtle and watch it on the job. The turtle is working really hard to create the centers of the spiral. Let's try another view and remove the turtle and instead draw every line segment in a different color. This way, we can better see which segment is replaced at any given step of the drawing. Or maybe even better, we will zoom into the bottom right part of the image and slow the turtle a little more down to understand what is happening in the very center of those spiral ends. When looking more closely, we can see that at the iterations around 45 degrees, the turtle draws an octagon. But as we can see, due to the change in angle, the corners do not match up. We rotated 364 degrees to complete the octagon on iterations 42 through 49. The same happens for the hexagon at around 60 iterations, the square at around 90 iterations, and the triangle at around 120 iterations. When reaching iteration number 180, the turtle will just turn around and start retracing its steps, until it is back at where it came from, but now facing in the opposite direction compared to the beginning. In the end, it will take the turtle 720 steps to complete its journey of the base element once, while visiting every point on the base element exactly twice. So when do we get a base element, meaning a basic Euler spiral? Generally, this is true whenever 360 degrees divided by theta result in a whole even number. So with 4 decimal places, we find 98 base elements, including the very high theta values like 60, 90 and 180. These do require some fantasy to see the Euler spiral in some triangles or steps. Still, I really like how stepping through the theta values allows you to see the base element unfold into a single straight line. And there are plenty of variations that do return to the origin and are artistic variants of these base elements. And base elements of base elements and base elements of base elements of base elements. You get the point, and very shortly we run into the doom of floating point calculations and precisions and have to be very graceful in detecting the origin return. I was long asking myself if all of the turtles will eventually return home, until it struck me that for theta equals to 0, the turtle will take off and search for infinity. So we have established that cases exist where lines are formed. And also, when 360 divided by theta results in a whole uneven number, a straight line of base elements is formed. They all need to be corrected by rotating the turtle before takeoff to fit properly on the screen. The first line meeting this criterion is the theta equals 120 degrees line. It is barely a zigzag line. It is followed by the 72-degree line that looks like being constructed of triangles. With the 40-degree line already resembling the base element as we know it, the smaller theta gets, the more elaborate the Euler spiral is formed. During my search, I stumbled upon some theta values that seem to form a straight line, or at least during the first couple million steps. Even though they all look like lines, some deviate from the center despite all the automatic correction I applied. So some of these lines might just be large superstructures, but they are still beautiful and nice to watch running across the screen. The created images are symmetrical to each other when moving clockwise and counterclockwise through the 360 degrees of a circle. For those theta angles where the turtle does not return home, the images are mirrored on the vertical axis, while for those theta angles that form lines, the image is flipped on the horizontal axis. When exploring the theta space and looking for new structures and images, we only need to explore 180 degrees of the theta space to get an idea of the full picture. Here, all the angles between 1 and 179 are shown side by side together with their counterparts on the other side of the circle for the appreciation of the symmetry. But the theta universe does not get any smaller by this, as there is a lot to discover in smaller and smaller theta fractions. Like Feynman said, there is plenty of room at the bottom. During my exploration of the theta space, I was always looking for a way to predict when the turtle will be home latest. It helps predicting calculation time and having some fresh salad in the fridge. I tried a lot and finally came up with the following approach. First, let's talk about those angles that form a closed loop and split a circle into a number of equal pieces. I named them the dominant angles delta. These can be compared to the dominant frequencies in sound wave analysis. Each theta can be represented as a sum of dominant angles, and for every dominant angle, we know exactly after how many steps a full circle is completed. Here's an example on how to estimate when the turtle will be home. The dominant angles for theta equals 6.609375 degrees are 6 degrees, 0.6 degrees, and 0.009375 degrees, splitting the circle into 60, 600, and 38,400 pieces respectively. The lowest common multiple is 38,400, as it is divisible by 60 and by 600. If we were just running in a circle, turning 6.609375 degrees per step, the turtle would be back home after 38,400 steps. But as we do not turn 1 times theta per step, but the current step number times theta, we need to apply Newton's formula to calculate the sum from 1 to 38,400 multiplied with theta, and then look at the decimal rest when dividing by 360. The rest is 0.5, meaning the turtle did half a turn. So to be completely home, the turtle needs to take these steps twice. The upper limit for the turtle to be home, given that this formula is correct, is after 76,800 steps. This is the same situation we have established for the base element with theta equal to 1 and 2 times 360 steps. Experimentally validated, this seems to be the upper limit for the turtle to be back home latest if it's not on a line, but sometimes the turtle is home early. To find these possible points of early return, we take the prime factors of the upper limit and combine them in a way that new combinations satisfy the boundary condition that the turtle angle needs to be returned to 0 after taking all the steps. As we already had to multiply by 2, we know that we need all the 2's. but we can remove the 3 and both 5s for this criterion to hold in some cases. So our final estimation gives us 1022, 5120, 15,360, 25,600 and 76,800 as possible return steps for the turtle. In the case of theta equals 6.609375 degrees, the turtle is home after 5,120 steps. Experimentally, this estimation seems to hold, and I have tried thousands of theta values. For lines, this algorithm makes it easier to find the point where one base element of the line is finished. But it is the result of a lot of guessing, and I cannot prove it. Nevertheless, it helps me plotting new t-shirts. With the study of larger angle thetas, I currently assume that all turtles that do not deviate to infinity will eventually return home, but as I said, this is currently only an assumption. Thank you very much for watching this video and your interest. If you found a mistake or have further ideas, feel free to comment below. If you liked this video, give some love to the Numberphile team and especially Brady and Matt. Without them, this would not have happened. To cite Matt Parker, the terrible Python code is over on GitHub with a link in the description. And now I will leave you with some of the animations that I just found to be beautiful.